Variance of a random.
Continuous random variable. Can you explain that again?
Yeah. So what happened to that? Huh? Here. Here you're asking a question here.
Yes, Professor.
So first thing, did you find expected value of x? Hello? Hello?
Yes, Professor, I can hear you.
Yeah, so first thing, we have found expected value of x. Okay, now you need to find expected value of x squared. How do you find the value of expected value of x squared? Look how we found expected value of x. So how do you find the expected value of x squared?
Professor, your voice is breaking.
Was that?
Sir, we can hear you twice, like whatever you're saying.
Twice.
Because Afia's
Yeah.
microphone is stuck on
Uh,
that's why.
Let me, in that case,
Afia, can you just turn off your microphone? It would be okay.
if I turn off my microphone, how can you listen here?
No. I'm saying Afia's microphone because Afia's microphone was on. That's why we are hearing your voice
Arnika,
twice.
yeah, who is speaking? Arnika speaking?
Yes, Professor.
Okay. So I don't know what.
So now it's okay.
Now it's okay.
Now
I
it's
think
okay.
it's the other student. Yeah. That's why it was disturbed.
Please mute yourself. Everybody else, mute yourself. Now is that okay?
Yes, Professor.
Yes.
Professor.
So which yours? Let's see. Now, can you see this screen? Hello?
Yes, Professor, we can
Okay.
see.
So if you know x values, okay, you want to know the variance of x. Is that what your question is? Faiza? Who asked
Yes,
that?
Professor. I wanted you to explain the formula for variance. Like,
The formula for variance. Yeah.
yes.
Yeah. So here it's a square. I don't know what's happening. Yeah. So it's saying variance of x is actually expected value of this square, x minus mu. What is mu? Mu is the mean of random variable x. So basically what you are doing is you are trying to find the deviation from its mean. Okay. And deviation from mean is obviously you square that and the expectation, and then it's a kind of an average dispersion. So what is a variance? Variance is a dispersion, measure of dispersion from mean. So dispersion here x minus mu. So deviation from mean, and you square that and you take some sort of average, expected value. So it's kind of an average dispersion. How do you find that? Is a shortcut here, or you can right away you can do this, but it's a shortcut here. You have this expected value of x already. Now you find expected value of x squared. How do you find expected value of x squared? Expected value of any random variable is, remember that column. Which column? Here, here. Expected value of any random variable x multiplied by probability of x, and you add that column. So it's the same thing. Here. So you square x, you have x values, you square that, and then you multiply that by probability of x. So if you want me to do it here, let's do it here, okay? First find expected value of x squared. Oops. Now this is the variance, as we know. We want to find expected value of x squared. Equals what? How do you find that? You find x squared. So x squared, this will be equals how do you do that? Expected value of x, and you do expected value of x squared. I'll copy it from here. However, you will have, instead of x, you will have x squared. Can you find now? Hello?
Yes, Professor.
So you find expected value of x squared. Then if you find expected value of x squared from here, just follow this rule. Then you have expected value of x here, which is 9/4. Then you will find expected value of x squared. Take the difference, that gives you variance of x. I hope you try, but don't forget that this variance is a measure of dispersion. Can I ask one question here? Hello? Hello?
Yes, Professor.
Okay,
Yes,
so why are they taking square when they are doing the variance? Have you ever thought of that? You see that is a average of expected value of x minus mu whole squared. So x minus mu is the deviation, okay? And you are squaring that. Why? No answer? Nobody wants to say anything? Some people quickly left the class. Faiza binte Harun. Are you there? Hello, Faiza.
Yes, Professor.
Why do you think they are squaring this deviation?
To remove the negative value.
Exactly. Some deviations are positive, some other deviations are negative. Some values are higher than mean, some values are less than mean. So there are some positive values. Some of them are negative. So when you take square, you get rid of all the negatives. Then are you making a mistake? Squaring the deviations, aren't you inflating the dispersions? Hello? Are you inflating the dispersions by squaring? Why is nobody speaking at all? Alma Chaudhary. Alma Chaudhary? Hello, Alma. You just logged on? Are you still there? Okay.
Professor.
Yes, Alma. Hello, Alma. Hello. Inara Al-Wasuf. No response. Jebun Nessa.
Yes, Professor.
Jebun Nessa. Okay, finally I found somebody. Jebun Nessa, what do you think? When you are squaring the deviations, true, you are getting rid of negative signs. Aren't you inflating at the same time, increasing the deviations, the mean and all this?
Yes, Professor.
So, is that a good thing?
No, Professor.
So what do you do?
Because it's negative sign, that's why it's not a good thing.
Huh? Have you ever thought of this? Do they have any remedy for that?
Professor, can I try?
Yeah. Who is speaking?
Professor Naushin.
Naushin, yeah. Go ahead, Naushin.
Professor, we are not inflating because we are subtracting expected value of x from expected value of x squared.
Oh, that's why you think we are not inflating. But what is that? That is just a shortcut of this one. Okay, this is what you are doing. What are you doing? You are taking the deviation from mean. Here is the mean, mu x. And how many values do you have? Hello? Depending on the values your variable is taking. Here, infinity values from 0 to 3. So, some values obviously are below the mean, some other values are above the mean. So, some deviations are negative, some deviations are positive. When you are squaring, aren't you increasing the values? Let's say deviation is minus 2. What is the square of that? 4. Deviation is 2. What is the square of that? 4. Deviation is minus 3. What is the square of that? 9. So, and so on. So basically what I'm saying is, yeah, you are inflating, but they have a remedy for that. What they are doing is, after finding the variance, they are taking the square root of that. Positive square root. What is it called? Positive square root of variance is called
Standard deviation.
Standard deviation. So once they have squared all the values, so at the end of the day, they try to take the square root, which is standard deviation. So that's one way, and it has good properties. That's why they are resorting to that. What other way could there be to get rid of negative sign? Huh? Hello guys, you have done probability statistics. The deviations, some deviations are positive, some deviations are negative. To get rid of negative values, or else it will be misleading. That's why they square it to get rid of negative. What other ways are there? Huh? People are leaving when I ask questions.
No idea.
Yeah, another way is to take the absolute value.
Just ignore the minus sign.
Yeah, take the absolute value of the deviations. There is one measure. Depending on that, using that absolute values, you should have known. But this variance or standard deviation, it has more desired properties than that one, the other one. That's why they use the variance or standard deviation. Anyways, that's beyond my thing. But you should always read between the lines. When they do something, you ask why are they doing it. So then we talked about this continuous variable, very simple continuous variable within the range.
Hello.
0. Yes. Hello.
Professor, can we directly write variance of x equal that e of x square minus e of x to the power, like e of x square?
Yeah. That's a workable formula. You can use that. But I was asking a deeper question. Why are they taking square? Yeah, to find the variance, you can directly use it. Okay.
Okay.
All right. So then this simple continuous variable with a density function 1/9 x squared. You can find the mean, you can find the variance. Also, you can find the probability over a range. So what is the probability? Let's say, for example, I kind of wrote it here. What is the probability that x lies between 1 and 2? How do you find that? So you want to know the probability that you pick a value of x that lies between 1 and 2 over this range. How do you find that? You integrate the density function, but it's a definite integral from 1 to 2. So here is the density function of x, density function of x, and you are asking a question. What is the probability that x lies between 1 and 2? How do you find? It's basically the area under that density function. If you recall your calculus 1, you know that definite integral is measuring the area under a curve between two values. So that's what you are doing here. You are measuring the area under the density function between two values, 1 and 2. That will give you the probability of x lying between 1 and 2. So that's what. Probability that x lies between 1 and 2 is nothing but a definite integral, goes from 1 to 2, and that the integration of that density function, which is 1/9 x squared. And you do the math and you get something. Obviously, it's less than 1. And question. Everybody with me here? How to find the probability that a continuous random variable lies between two values? Huh?
Yes, Professor.
So I hope you all are on the same page.
Yes.
So how about this? What is the probability that x lies between 0 and 1? What do you have to do?
Integrate
Yes.
by taking 0 to 1
0
range.
to
1.
1. So, and again, between 1 and 3, integrate between 1 and 3. And how about this? Last one.
It lies
Huh?
between 0 and 3.
What is the probability that x lies between 0 and 3? Huh?
Integrate from 0 to 3.
What do you get?
We need to calculate.
Yeah, we need to calculate it.
You need to calculate, or you look at the density function. Here is the density function. Can you tell now? Do it then. From 0 to 3. Take your note, do it.
Professor, is it 9 by 4?
No, do it.
Yes, Professor, I have done it in the last class.
No, not last. Do it now.
I have already done it, Professor. The answer is 9 by 4.
9 by
4.
4.
Yes.
That's wrong then.
Wrong?
Anyway, so we'll come back to
Give us
that.
time.
Huh?
Professor, give us time to solve.
Okay, I'll give other problems. Let's go ahead with our actual thing. What is my goal here? So there is now the most important thing here today, and maybe from the rest of your life. No, that's an exaggeration. But at least if you stick to economics or anything, finance or anything like statistics, you will come back to this thing. It's called normal distribution. So what is this? It's a distribution of a random, continuous, random variable. Okay. And so if it's a continuous random variable, it has a density function. Who recalls the density function, normal density function? Anybody?
Yes, Professor.
Huh?
Yes,
Go ahead.
Professor.
Go ahead. Let's see.
It is 1
Yes.
by root over 2 pi sigma square
Exactly.
to e to the power minus
minus
x minus mu divided by sigma whole square.
Yeah, e to the minus half x minus mu over sigma whole square. Yeah, I still remember this. So thank you that you remembered this ugly thing. But this normality, see, the name indicates if it's normal, then how about the other random, continuous random variables? What do you want to call them? Huh? What do you want to call the other random variables, continuous random variables?
Only continuous.
No. Yeah. So what I'm saying is if it's normal, then others might be abnormal.
Abnormal.
No, I'm just kidding. But there's some truth in that. Any other continuous random variable distribution of other continuous random variables will be compared with this one. Normal distribution. Normal distribution is actually a natural phenomenon. I don't know why. It looks like most variables, if you give enough number, most variables are normally distributed. In public health, in economics, in finance, in most of the cases, even they say some the blood cells and all these are normally distributed. Now that's why we have to spend some time on the normal distribution. Normal distribution is a continuous random distribution. It has some very good properties. And any other distribution, continuous distribution, obviously you will be always referring to continuous most of the time. You have to compare with the normal distribution. What is so special about this distribution? This distribution is a very symmetric. It's a perfectly symmetric distribution. The density function, it looks so ugly however, when you draw it, this is a perfectly symmetric distribution. That means that means a lot of things. First thing is its mean is in the middle. So mean and median and also the middle things happen most often. So the model value, they are all same. Let me share the other from our book. Let's share the book. So here, the normal distribution. Can you see the book?
Yes.
Yeah. Most important thing on earth is the normal distribution. Look at the density function. So if x is a continuous random variable, it's said to be normally distributed if the density function has the following form, as you said, 1 over square root of 2 sigma pi square e to the minus half x minus mu sigma square, and this is here a whole square. So it's this. So this is the density function. The values, so one by one, as far as we is important for us. We will, and if you have questions, if you ask difficult questions, don't ask me. Ask your probability statistics professor. So the values of a normal distribution can go from negative infinity to positive infinity. Okay. So if you said this is a normal distributed, random variable is normal distributed, the range is minus infinity to plus infinity. So that's one. It's symmetric around its mean value. Symmetric. Here is the symmetricity. You can see it's called bell shape. Anything else you have to compare with this. There is the bell shaped. This is if you believe it or not, this is the graph of that ugly density function, and you see the mean is exactly in the middle of two tails, and that is so mu is the mean, variance sigma square. Look at the where am I? Here. So here is the bell-shaped distribution, and you can see that this is the mean value. So what are you doing on the vertical, on the horizontal axis? What are you measuring? Hello? What are you measuring on the horizontal? Is this line?
Standard deviation.
No. I'm saying
The parameters.
so. This line. What are you measuring here?
The parameters, population parameters, maybe.
You are so this is the density function, okay?
Yeah.
Huh?
Yes.
So what is your x-axis and what is your y-axis? For the
X-axis.
huh? Come on. You are drawing the density function. Then you are saying the horizontal axis. You don't know?
It's the.
You have to be confident about this.
I'm not sure, Professor.
Why not? What did you do in the probability study? Did you do
We
this?
just called it X and Y.
Yeah. What is x there? What is the x there?
It's minus infinity to infinity.
Yeah.
right?
What are they? What are they? They are the values of your variable. On the x-axis, you are measuring the values of your variables. How many values a normal variable can take?
Minus infinity to infinity.
Plus infinity. Infinity values, starting from minus infinity to plus infinity. So in the x-axis, what are you measuring?
Variables.
The values of the variable here. Let's say is the height of the people of Bangladesh. So what are they? Give me a number then. What are the values here?
Minus 3 sigma, minus 2 sigma.
Minus 2 sigma. What are you saying? Minus 3 sigma. The
0, 1, 2, 3 or 10.
0. What is your unit of measurement?
Centimeter.
Centimeter. So, what are the values? Huh? Give me reasonable values. Some reasonable values.
100. If
100,
it's
0.
110,
Yeah.
and all the values here of your height. Height, if it's a normal distributed distribution variable, then these are all heights. Okay. If it's a weight, these are all pounds or kilograms. If it's normal distributed. What else? Give me another variable which is normal distributed.
Time.
Time of what?
Time, like, or else distance.
Distance from where?
Sorry, Professor, I didn't get you.
Okay. So I'm saying there are a lot of normal distribution, normal variables. Normal variable meaning it's a continuous random variable with this particular density function, and here on this x-axis you are measuring those values here. If it's height, its weight, its price of your rice, or if it's the GDP of different countries, then this is the dollars, and so on. And what are you measuring on the vertical axis? Remember, it's a Cartesian space. Euclidean.
mean.
No. What are you measuring on the vertical? Is there a vertical axis?
Yes.
Yes. So what
Standard
are
deviation?
you are measuring standard deviation on the vertical?
No.
Are you serious? Are you
That's in the horizontal. I'm sorry.
horizontal? You are doing all the values, okay, of your random variable, which can go from negative infinity to plus infinity. Now, what are you doing on the vertical axis? I'll ask one by one. Please don't leave the class, okay? Just kidding. I know you guys are smart and you know how to do it. The Dema done, I guess you have some good idea about probability statistics. Dema? Hello, Dema.
Yes, Professor. Professor, can
Huh?
you repeat?
What are you measuring on the vertical?
Become. Hmm?
Huh? Loudly,
What's your
please.
question, Professor?
What's my question after all this? The question is, if this is the so-called density function here, you are graphing, you are drawing, and you are saying here the x values, and here on the vertical axis, what are you measuring there? How did you draw this line?
Is it the expected value?
Huh?
Is it the expected value?
Expected value? Expected value is only here. Do you see that mu is here?
Yeah.
So that's this on this line. On this line, on the horizontal line, you have one point on the line, which is mean.
Professor, is it the density function?
Exactly, is the density. Is the density. So any point on here, how did you get this? How did you draw this curve? Huh? You have drawn this curve. If you know mu and sigma square, okay. If you know, you see, look at this density function. You guys should read between the lines. Where that's why probability statistics is a must for this class. If you look at this density function, if you know mu, if you know sigma square, what is mu? Mean of
Standard deviation.
this random variable x, expected value of x. What is sigma square?
Standard deviation.
Variance of x. These are called parameters, mu and sigma square. They are called parameters. If you know mu and sigma square, do you see that you know everything about this function? Do you know pi?
Yes, 3.14, right?
3.14 blah blah. You know 2? Yes.
Yes.
Square root, you can square root it? Yes. Only if you know mu and sigma square, then you know everything about this density function. X is the variable values. How many values are there? Millions of values. So then if you know mu and sigma square, you get the millions of values of the function, density function. Okay? Are you guys okay with me? You think about it. The beauty of normal distribution is if you know only two things, mu and sigma square, you know everything about the density function. Then for each value of x, you know the density function, that then you plug that value of mu and sigma square. Let's say x equals something here, 999. You plug the value 999. You know mu, you know sigma square, then you know the height of this line. So for each value of x from the function, you know the height. So what is the height of this line telling you? Hello?
Yes, Professor.
What is the height telling you?
The density function.
The density function. The density of each value, the density of each value. And I'll not go deep in that if I let you think about it. So this whole curve is known only if you know mu and sigma square. Two things you know everything. Then if you want to know the probability that x lies between two values, what should you do? Let's say you want to know the probability that x lies between 55 and 99. What should you do? What can you do? No answer? You just did it. You just did it. We just did it a little while ago. Well, what is the probability that x lies between 1 and 2? What did you do?
Integrated.
You integrated the function, the density function over that range. In terms of curve, what does it mean? In terms of this curve, you basically are looking at the area under the curve between these two x values. Is that true?
Yes.
Definite integral means what? Area under the curve between these two values. That's what you can do here. So any probability you want to know, if you know the density function, obviously you have to know mu and sigma square. If you know the density function, then you integrate this density function over that range, let's say 55 to 99. You can integrate this function, you get the probability. But if you can draw the graph from that density function, that is nothing but the area under that two values of x. Ask any question about this. Fundamental ideas. Question? No question. Okay. In that case, we move on. We say this density function is the most beautiful thing in the world. Why? This is symmetric around its mean. The mean here also, if this is the mean value, that is also the median value, that is also the model value. It's so symmetric that if you can take this curve, take it out and impose it on this, it will be exactly same. That means this area and that area is exactly same. I hope you have heard of this thing. Maybe sometimes you did not realize what you are actually learning. So what is this whole area under this curve? What should be the area? Hello?
Yes, Professor.
What should be this whole area? Yes, thank you. 1. Because probability that x lies between negative infinity to plus infinity will be, all probabilities together will be equal to 1. So the whole area is 1, and then half of the area from mu to right side is 0.5, from mu to left side is also 0.5. Question? Hello?
No.
Are you guys okay?
Yes, Professor.
All right. So that is the, I'm giving some time on normality because normality is so important in your future life. If you stick to economics or statistics or finance, every time you come back, you refer back to normality. So you should understand this thoroughly well. And so even though number 2 is an interesting, beautiful property of normality, even though the values of x can go from minus infinity to plus infinity, however, most values lie around the mean, around mu. Most values lie, and you will be amazed if you think about it. If you go one standard deviation to the right and one standard deviation to the left, plus minus sigma, mu plus minus sigma, that will contain 68% of total values. Remember, the values go from minus infinity to plus infinity. However, only if you can cover plus minus one standard deviation, actually you are covering 68% of the values. Can you imagine? Let's say mean is 60 and standard deviation is 5. So from 55 to 65, this range will cover 68% of the values of the variable. Even though if you consider all values, they can go from minus infinity to plus infinity, but most values are here. 2 standard deviation, mu plus 2 plus minus 2 sigma, 95% of the values. So this area here, from here to there, actually 95% of the values are there. And if you take 3 standard deviation, almost everything there, 99.7%. And in the tails, left tails or right tails, very, very few values, very few values. Most values are focusing, concentrated here. So that's the beauty of normal distribution. So even if the values can go from negative infinity to plus infinity, if you can focus on the center around the mean, you are actually looking at most of the values. Okay. So you want to know probability of value lies between x lies between 2 values. One's pretty standard, straightforward way is to integrate. Take a definite integral of the function. If you know mu and sigma square, you get the probability. Or if you have this graph, you get the area under that 2 values. Area under this curve between those 2 values of x. Now the problem is this is normal. However, the curve is bell-shaped, symmetric, and all. However, the curve changes with mu and sigma square. These are 2 parameters. If mu is different, you get a different curve. Then probability changes. If you get a different sigma, the curve changes, and you get different probabilities for different ranges. So because this normality depends on only mu and sigma square. So different set of mu and sigma square, different density function, and different curve, density curve, and different probabilities for 2 different values, 2 different areas. That's the problem. Any random normal distribution you bring, you have a mu and sigma square. If they are, so if I bring one with some mu and sigma square, you bring another one with another pair of mu sigma square, totally different curve. Obviously, each of the curves is bell-shaped, symmetric, and all these properties, general properties remain, but area between 2 values for 2 curves will be different, meaning probabilities are different. So to get rid of that, I hope you understand, you know this standardization of a distribution. For any distribution, not only normal, you can find a new variable. It's called standardization of a variable. So if x is a normal distribution, you can standardize it and you get a standardized normal variable, and conventional is called a z distribution. How do you get a standardized normal variable, or for that matter any standardized variable? This rule, never forget this rule. To standardize a variable, what you do is the variable minus mean of the variable divided by standard deviation of that variable. See, here we have this x normal distribution, x variable. We subtract its mean, x minus mean of x, not mean of something else. X minus mean of x divided by standard deviation of x, not anything else. This mu and sigma, they are mean and standard deviation of x variable. So how do you get a standardized normal distribution? If x is a normal distribution, you subtract mean from each of the x value and divide the deviation by standard deviation of x. Are you okay? Hello?
Yes, Professor.
Professor,
Professor, can you
Yes.
repeat it again?
Yeah.
I have a question actually.
Yes.
Professor, like if I compare this one with the normal distribution formula, so there is no sigma square under the root, and there is
Here.
yeah. Why so?
We are coming to that. First thing. So we all know how to standardize a variable. The variable minus mean of that variable divided by standard deviation of that variable. Any question about that? Hello? Hello?
No, Professor.
No.
Yes, Professor.
If there's no other questions about how, I'll ask this question again and again. You can never forget it. How to standardize a variable. Never forget this formula. Variable minus mean of the variable divided by standard deviation of that particular variable, not other variable. Sometimes people divide by some other standard deviation. No, you have to find the standard deviation of that particular variable. So now somebody asked why if x is normal, z also a normal distribution. Okay, if x is normal distribution, z is also normal distributed. Now where is sigma and in the density function? Where is sigma and where is mu for that matter? You have lost mu, you have lost sigma from here. Why? Because this z is a normally distributed with mean 0 and variance 1. What did I say? If you standardize a random variable which is normally distributed, you end up with a standardized normal variable z. But what is the mean of z? Expected value of z is 0. Variance of z is 1. That's why. So you plug, if you plug, so instead of x, you write z. What will be sigma? What is the variance of z? 1. So 1 vanishes. 1 vanishes. What is the mean of z?
0.
0. So here you see no mu because mu is 0. No sigma because sigma is 1. So here z has 0 mean and unit variance. Is it normal? Yes, it's normal, but it has a particular. Any random normal variable you are given, you standardize it. How do you standardize? Variable minus mean of that variable divided by the standard deviation of that variable, and you do it in a way that you get another variable z, which is normally distributed with mean 0, variance 1, and then if you can, then obviously the density function is given here for z. For any normal distribution with mean and variance, as I said, I bring one, you bring another one, normal distribution. Mean is different, variance is different, but we can convert that into Z. And then this density function is known because everything is known here. You see, everything is known here except for the value of Z. So this density function is fixed. The curve for this density function is fixed. So it's always same. The area under two values of Z is always same. Area means the probability. So probability that Z lies between any two values remains the same always. Do you see the advantage of that Z? Hello?
Yes, Professor.
So that's why Z is kind of invented. Yeah. Z is invented because the density function is known, it's always the same, and the probabilities are known and they are given on a table. I hope you all have seen Z table. Did you see Z table? Huh?
Yes, Professor.
Yeah,
Yes,
so
Professor.
there is a table at the back of this book. You can check. In the next class, we will do some simple example of how any distribution, normal distribution, can be converted to Z, and you find the area under the curve. Remember that the straightforward way is to integrate the density function, which means basically area under the curve between that two values. And equivalently, people did the menial job. They reported the probabilities in the table and we just use them. But never forget that how they got the values, probabilities. Question? Hello? Any
Yes,
question?
Professor. No, Professor.
All right, then I would say, what time is it? My clock is not. What time do we knock off? I think we have some time. Yeah, we do have some time. So, normal distribution. Any question about normal distribution? Shoot now. Here, you see, so there is an example of how they are changing. Let's say, assume X is a normal distribution with, this is how they write. Now, this is how they write. Okay, this is by convention, this is how distributions are written. X, so when you see X and a curly thing here, and N for normality, and first one is mean, second one is variance. So how do we read this? X is normally distributed with mean, mu, and variance, sigma square. It's just telling you that X is a normal variate. X is a normal variable with mean, mu, and variance, sigma square. And standardized normal variable, Z is, though they wrote it X, actually say, yeah, it's the normal Z variable Z. It's also, how do you read this? If you write Z here, how do you read this? Can anybody read it for me? Yeah, go ahead.
Z is a normal variable with mean 0 and variance 1.
Variance 1. Remember, first one is mean, second one is variance.
Variance.
Yeah, N stands for normality. So there is an example, simple example you did in the probability statistics. I guess you did millions of examples like this. So I'll show it from the book. Assume that X is normally distributed. Somebody read it for me. Hello?
Assume that X is normal distributed between mean is 8 and 4 is variance. So
Yeah.
what is the probability that x will assume a value between x1 equal 4 and x2 equal 12 to compute the required probability.
Okay, hang on. So here, x is a normal distributed with mean 8 and variance 4. By the way, are they sampling mean or population mean? Sampling variance or population variance? Now everybody is quiet.
It's population variance.
These are all population parameters, mu, sigma square. When you see mu, when you see sigma square, be alert. They are population parameters. Mu is expected value of x, population mean. Variance is expected value of x minus mu whole square, population variance. There is no point of sampling mean and variance here. Sample will come later. So if x is normal distributed with population mean 8 and population variance 4, you just want to know what is the probability that x lies between 4 and 12. One way, the long way is to do what? Is to integrate the density function. Where mean is known, sigma is known, you integrate that function between 4 and 12, and it's a definite integral, you get the value of probability. However, this z is giving us, an opportunity of doing it a shortcut. What do? You convert the values into standardized z. So you convert 4 into z. How do you standardize? Variable value minus mean divided by standard deviation. Value is 4 minus mean is 8 divided by, if 4 is the variance, standard deviation is 2. Square root of 4 is 2. Then you get minus 2. Then another value is 12. So you also convert that x 12 into z. 12 minus 8. What is 8? The mean. The standard deviation is 2. You get plus 2. So basically what you want to know is the probability that x lies between 4 and 12, which is exactly equal to probability that z lies between minus 2 to plus 2. What is the mean of z? Hello?
Yes, Professor.
What is the mean of z?
The mean is 8.
Z, not x.
Oh, minus.
No, you just forgot. Z is a standard variable mean
0 and 1.
0 and variance 1. You cannot forget that. Standardized normal distribution. So the mean of z is 0. So basically what you're looking at is, what is the standard deviation of z?
1.
1. So what are you looking at here? 0 is the mean, right? To the right, how much you are going? Think about that density function, that nice, well-behaved shape, very nice distribution. Where is the mean? Mean is in the middle.
Yes.
0 is in the middle. And how far you are going to the right of the mean?
Over here it seems like
Plus 2. What is the standard deviation of z?
1.
So how far you are going? From 0?
Variance is 1.
Yes, so variance is 1. So what is standard deviation?
Also 1.
That will be 1. Yeah.
So from mean, how far you are going to the right?
1.
1.
2.
Yeah, here is 2. Can't you see 2?
Yes,
Can you see
Professor.
2?
Professor, I already said 2, but you.
Yeah, so but how far? In standard deviation terms?
3.
2 standard deviation. You are going
2 standard deviation.
2 standard deviation to the right, because 1 standard deviation is 1, 1 plus 1. 2 standard deviation, you are going to the right. And to the left of mean, how much are you going? 2 standard deviation. Because standard deviation is 1. So 2 means 1 plus 1. What is 1? 1 is the standard deviation here. So you are going for z, not for any other normal variable. For z, sigma equals 1. So 2 means 2 sigma. Minus 2 means that is also 2 sigma. So from 0, you are going 2 sigma to the right and 2 sigma to the left. What is that area? Without looking at the table even. Look at this. 2 sigma and 2 sigma. What is the area?
95%.
Huh?
95%.
95%. So what is the probability? Almost 95%. Probability that z lies between -2 to +2. See, almost 95% here. But if you look at that table, you get some little bit discrepancy. Is an approximation. But how to look at the table is another story. We will spend some time on how to look at the table. Each table is different. You can use your own table, or you can use the table from this book, or I can send some table from the online. Each table is different. You use your own table for the exam. I'll teach one of the table. I'll show you how to read the table, anyone. And if you like that table, you use that, or you use your own other table. But don't ask me in the exam, Professor, how to read the table. I cannot do that. I'll do it in the class. So. Question. Hello. No questions? I have no questions. Oh, there is a comment on the chat box. No. This is an everyday problem. You have to be in within 15 minutes. Okay. Today is the last day. Please, Farishta, take this lady, Monica.
Professor,
Yeah.
Professor,
Yes.
when I took the attendance, it was 5-5 and there were 42 students, but now there are 40 students.
Oh, some people.
So if I take the attendance now, those 2 people will go.
Okay. Maybe you can just manually for last day. Okay. I know it's bothering people. You cannot just walk into the class. You please enter within 15 minutes. Don't show me excuses. I cannot solve that kind of problems. That's not my job here. I have to explain these things, difficult things to you. If you have other issues, you talk to TAs, okay? And we can figure it out.
So during class time, sometimes we are facing electricity
Class time is
problem.
up.
That's why we got disconnected.
Yes. Class time is up. Okay. In that case, we call it a day. We'll come back on Tuesday. Please read the book. All right.
Professor.
If class time is up, I'm just leaving right away. You have issues, you email.
Professor, I have a question regarding this course.